In the previous class, we calculated force on a charge due to a collection of charges, and we use principle of superposition. In this class, we will calculate force on a charge Q due to distribution of charges. By distribution, I mean it could be a charge distributed over a line, and this I will say charge per unit length will give me the distribution. That charge could be dependent on which position I am on, or it could be independent. There could also be charge, say, on a ring or on a disk. Here again I will say charge per unit length, which is usually denoted by lambda, or charge per unit area, or charge in a volume, which will be charge density, charge per unit volume. This is known as the charge density. This is known as surface charge density. This is linear charge density. So, let us consider these cases. To start with, let us take a line charge extending from minus L by 2 to L by 2. So, that its origin, center is at the origin. Let this direction be y, and I want to calculate force on a charge q kept at a distance x from the origin. The line charge I will denote by a different color. So, let me denote it by red. This is the line charge, and let its magnitude be lambda per unit length. Then, as we did in the case of collection of charges, let me take a small element of length dy at this point at a distance y from the origin, and calculate the x and y component of the forces of the force on charge q. In this case, the distance from this element to the charge is going to be square root of x square plus y square, so that by Coulomb's law, the force on charge q F vector is going to be equal to lambda dy is the charge in this element here, q over 4 pi epsilon 0 1 over x square plus y square in the direction of x minus y over x square plus y square raised to 1/2, where this vector that I have written here, you can check, is this vector, and that divided by the magnitude gives me the unit vector in that direction. This indeed is the force direction. So, f x is given by the x component, which is q lambda over 4 pi epsilon 0 x dy over x square plus y square raised to 3 by 2. 3 by 2 comes by combining these two terms, and this is integrated from minus L by 2 to L by 2, which will give me q lambda over 4 pi epsilon 0, x will remain there. I am left with the integral to L by 2 dy over x square plus y square raised to 3 by 2. You substitute y equals x tangent theta, so that dy becomes x secant square theta d theta, and substitute this in the integral, and you are going to get f x is equal to q lambda x over 4 pi epsilon 0 tan inverse minus L by 2x to theta equals tan inverse L over 2x x secant square theta d theta divided by x cubed secant cube theta. I am going to cancel some terms. This x and this x cancels with this and gives me x only. This secant square theta divided by say cube theta gives me secant theta, which becomes cosine theta on top, and therefore, this integral becomes q lambda over 4 pi epsilon 0 tan inverse L over 2x with a minus sign in front to tan inverse L over 2x cos theta d theta, and this immediately gives you answer, which is 2 q lambda over 4 pi epsilon 0. I am sorry, there was this x here also. So, this x here sine of tan inverse L over 2x, which actually becomes, again I cancel this 2 with this and give you 2 to get 2 q lambda over 2 pi epsilon 0 1 over x sine of tan inverse L over 2x is going to be L divided by square root of L square plus 4x square. That is the answer for f x. How about the y component? The y component is going to be f y equals q lambda. You can check that I am writing the expression from the previous slide, 4 pi epsilon 0 instead of x, because now I will be taking a component in the y direction. So, I will have minus y dy over x square plus y square raised to 3 by 2, and this is going to be from minus L by 2 to L by 2. You can see this is an odd integral in y, and therefore, this thing vanishes. So, on the line passing through the middle of a line charge at a distance x from it, the force on charge q is in direction x only, and its value is f x equals q lambda over 2 pi epsilon 0 x L over square root of L square plus 4 x square. As L tends to infinity, that means the line becomes of infinite length. You can see that f x goes to q lambda over 2 pi epsilon 0 1 over x, a well known result. Let us take example 2. For the second example, I am going to take, let me write example 2. I am going to take a ring of charge, again having lambda charge per unit length, and calculate force on a charge q kept at a distance h from the ring. Now, you see each element of this line charge is going to apply a force on this. Let us take two particular elements on the opposite sides, and I am doing it for a purpose. If I look at the force due to this element, it is going to be pointing this way, and if I take the force due to this element, is going to point this way. All the distances, this distance is going to be, suppose this radius is r, this distance is going to be h square plus r square. Similarly, this distance is going to be h square plus r square. So, the magnitudes of the forces are the same, and by symmetry you can see that their horizontal components are going to be in the opposite directions, and they are going to cancel, and it is only the vertical component that will survive. So, what I can do is, for each element I can take the vertical component, add it up. Let us see what the vertical component is going to be. So, the vertical component, the force due to this small element of length dl is going to be on charge q due to this charge lambda dl is going to be 4 pi epsilon 0 force magnitude times 1 over h square plus r square. Now, I take its vertical component. So, if this, let me erase this height now that it is clear what it is. If this angle is theta, so is this angle. And therefore, vertical component is going to be f cosine of theta, which by this triangle you can see is nothing but h divided by this distance. So, this is going to be q lambda over 4 pi epsilon 0 h divided by square root of h square plus r square, which will give me h square plus r square raised to 3 by 2, and there is a dl. Now, if I integrate this force, that gives me the total force. This integration, all the quantities q, lambda, this, all these are fixed. So, only integration comes over dl, and integration dl is really the length of the ring, which is 2 pi r. And therefore, the net force answer comes out to be only in the vertical direction is going to be equal to 2 pi q lambda h r over 4 pi epsilon 0 h square plus r square raised to 3 by 2. You can actually see that 2 pi r is the length times lambda is going to be the net charge on the ring. So, I can also write this as net charge on the ring times q times h divided by 4 pi epsilon 0 h square plus r square raised to 3 by 2. Notice, I am writing it on the left of the screen, that as h tends to 0 or it becomes 0, force is 0, which makes sense because the charge is right here. All the forces from all around are pushing the charge by equal amount. So, this is the answer. I can now use this result to calculate force on charge q on the axis of a disk, and that is going to be my example number 3. In example number 3, I am going to take this disk and put a charge at height h on the axis. I am going to use the result of previous example. In the previous example, what we saw is that the force on the charge is in the vertical direction, its magnitude is given by q over 4 pi epsilon 0 h over h square plus r square raised to 3 by 2. What I am going to do now is divide this entire disk into small rings. So, let us take a ring of radius r. Okay, so, I am taking a ring of radius r, width dr, and if the disk carries charge sigma per unit area, then on this ring the charge q is going to be, or let us say small differential charge dq is going to be sigma times 2 pi r dr. 2 pi r dr is the area of this ring, and therefore, the force due to this small ring, or let us write differential force, is going to be dq, which is sigma times 2 pi q over 4 pi epsilon 0 h over h square plus, now I am going to write small r square raised to 3 by 2, and there is a r dr, which is this term which I have written out here to facilitate integration. So, therefore, the net force, which is again going to be vertical, will be 2 pi sigma q over 4 pi epsilon 0 h integration r varies from 0 to capital R, r dr over h square plus r square raised to 3 by 2, And now, if I make the substitution, h square plus r square equals, let us say, y square, so that r dr is y dy, I get the vertical force to be 2 pi sigma q over 4 pi epsilon 0 integration. This integration is now going to be from h to square root of h square plus r square y dy over y cubed. This gives me y square, and I get 2 pi sigma q over 4 pi epsilon 0 1 over y with a minus sign h square root of h square plus r square, and that answer comes out to be, let us cut this also, 2 sigma q over 2 epsilon 0 1 over h minus 1 over h square plus r square square root, and this is going to be in the vertical direction. Notice, if r tends to infinity, this force goes to sigma q over 2 pi epsilon 0. If I go to the previous page, there was in this h also which I missed. So, there is going to be one h out here. Oh, sorry, next page. There is going to be an h out here. Let me show it by different color. The mistake I made, h out here, and therefore, the force becomes sigma q upon 2 pi epsilon 0. And that is the answer. So, I have solved 3 examples, simple examples of forces due to charge distribution.